Alrighty, Year 12 methods, welcome back. Oh, this exercise is differentiation of e to the power of x. This is probably one of my favourite ones to differentiate because it's pretty straightforward. So let's jump straight in. If you want to know what's going on in the background, as always, feel free to read the textbook. But ultimately, with this particular exercise, what you need to know is that if you've got the function f of x and it's equal to e to the power of x, then the derivative of that function is the same. It is e to the power of x. Perfect. That's pretty easy to deal with. I guess the catch though is when there is a like a constant or a k value in front of that x there. The thinking behind it does lie with the chain rule, but the rule ultimately comes out to being if you've got e to the power of kx and you're finding the derivative of that k value comes down in front, much like other things, but then the rest stays the same. It's still e to the power of kx. There's no subtracting one from the power or anything like that. Cool, so that's pretty fun. Now, putting it into action. It says here, find the derivative of each of these following with respect to x. Cool, you've got e to the power of 3x here. Happy days. This here is the k value. It's going to come down in front. Check. And we're left with the same bit here, e to the power of 3x. Done. Move on to the next question. This one here, we've got e to the power of negative 2x. Cool. Again, that's the k value. It's coming down in front when you differentiate it. Bang, that comes down there. And then the rest stays the same. Check. Oh, this is cool. We've got e to the power of 2x plus 1. Now, what you do need to know is your index laws with this. Yep. So when you have e to the power of 2x plus 1, it is actually the same as having e to the power of 2x multiplied by e to the power of 1. Yep. Now remember, when you have the same e here and you're multiplying it, it's the same with adding index laws. Yep. You add the indices. So you do need to remember from that. So as we said, splitting it up into e to the power of 2x multiplied by e. Perfect. Obviously, whether you write the e first or whatever, same difference. In this particular case from here, again, this is the k value that's there. It's going to come down in front, and the rest here is going to be the same when you differentiate it. Again, what you can do is then rewrite it using the index form. Yep. So that here you've still got e to the power of 1. Here you've still got e to the power of 2x. When you're adding the indices, they go together. Or when they're multiplying, you add the indices. This one here, no surprises. This here is actually the same as e to the power of negative 2x. Yep, and putting it back up on the top line. In that particular case, when you do make that change, obviously it's very similar to what was going on here. Well, it is the same as what was going on here with b. Yep. So we know how to differentiate that part. Here we know how to differentiate this. Oh, that was the same as part A. Cool, and they're making it nice and easy for us. So we're just doing that separately there. That's making sure that we remember what's happening. Alrighty, this one here, worked example number 26. It says find the derivative of each of the following with respect to x. Cool. Oh, this one here, we've got e to the power of x squared. Now, the good news is we just learnt the chain rule yesterday, so that will come into play here. So it says consider the following, making y equal to e to the power of x squared. Cool. But consider making this x squared part u, yep, as in the change rule. So it would be e to the power of u, yep, y equals e to the power of u. Applying the chain rule, dy dx is equal to dy du multiplied by du dx. Perfect. Dy du, we've made a note of. Du dx, we can differentiate that. 2 comes down the front, x take away 1 from the power. Again, we multiply them together as we're doing here, and we're resubstituting in what u was. So u in this particular case was x squared. So it'd be e to the power of x squared multiplied by 2x. Writing things out neatly in that order, we get that there. Cool. Same difference here. This one we've got e to the power of x squared, which was over here, plus 4x. Same difference, applying the chain rule, we get the following. Yep. Cool. It says here, find the gradient of the curve for y equals e to the power of 2x plus 4 at these particular points. So again, it's a matter of differentiating this, which we know how to do that process. Obviously the k value is 2, comes down the front. You're left with e to the power of 2x. So here's the derivative. 4, obviously, derivative of that is just 0. So what we're going to do is substitute in 0 into the derivative, and we find out that it is 2. So writing out what the gradient is at that particular point, you can say it is 2. Same difference here. This time we've got 1 as the x value and e squared plus 4 as the y value. What we're going to do is just going to substitute 1 into the derivative, which we've worked out before, and in this particular case we get the following. Worked example number 28. Cool. What's it say here? For each of the following, first find the derivative with respect to x, then evaluate the derivative at x equals 2, which we can do. It says given that f of 2 equals 0 and the f dashed 2 is equal to 4 and f dashed e squared equals 5, do the following. Perfect. Alright, so what we're going to do for this one here, it says let y equal e to the f of x and u be equal to f of x. So then using the chain rule, we're going to have y equals e to the power of u. And this does relate to this rule up here, which I sort of did skip over, sorry. So in general, if you've got h of x, so a function, and it's e to the power of another function, yep, so you got in the power, it is another function. The chain rule gives this here. So the derivative of this is the derivative of the function up the top. So you get the derivative of the function bit up the top, and then it obviously stays as e to the power of the function, what it originally was. Yep. Sorry, I did sort of skip over that a little bit. My apology. So in this particular case, applying the chain rule, which is listed there, you end up with e to the power of u and the derivative of f of x. And as this stays the same at the top here with u, it just stays as f of x. Yep. Once you've done that, you can substitute in x equals 2 into it, and showing that the derivative when e to the power of 0 multiplied by 4 is going to equal 4 here. Alrighty. Yeah, when we substitute 2 in, that's going to happen. Cool. This one here says let y equal f of e to the power of x. In this particular case, u is going to be this part here, e to the power of x. It says then, well, what we're going to do, we're going to have y is equal to f of u. So again, applying the chain rule here, we get the derivative of this, and it's multiplied by this here, du dx, which is obviously going to stay the same. Yep. Resubstituting in this here, and we get that. Again, you can substitute in x equals 2, and also in this case it tells us up here in the question when the derivative, we substitute in e squared into the derivative, it comes out to being 5, so we can use that to go from there. Alrighty, there is a summary here. I do wish you all the best with this exercise today. Have fun with that. Bye for now.